Welcome to section 2.5, the fundamental theorem of algebra. We will do a little bit of the 2.3 also in here with Descartes' rule of signs. We're still going to continue to work on finding all zeros of polynomial functions. A couple first things we just need to talk about. One called the fundamental theorem of algebra. It basically states that if the degree is greater than 0, then you will have at least one root in the complex number system. Now, complex number system includes real numbers and your imaginary unit or your complex numbers a plus bi as well. So we'll always have at least one root, if not more, in all the polynomials that we will be finding. The linear factorization theorem states that if f of x is a polynomial of degree n, where once again n is greater than 0, then f of x has precisely n linear factors. And once again, those factors in terms of those numbers, they can be rational, irrational, or complex as well in terms of the complex number system, so we can deal with that imaginary unit, but they can always be written as linear factors. And just a quick reminder, the roots of the polynomial can be real or complex and may be repeated, is what that's supposed to say, may be repeated, and that's that multiplicity that we have talked about. The next theorem that we'll be talking about is the complex conjugate theorem. Let f of x be a polynomial with real coefficients, which is the type of polynomials we'll be dealing with. If this is the case, if a plus bi is a root, then a minus bi is also a root. They always come in pairs, and that's called complex conjugates. This is always true when we have real coefficients of the polynomial. So in the first example, if I ask you to write a polynomial with roots 3 plus I and negative 2i, even though I only tell you 3 plus I is a root, you need to understand the complex conjugate theorem states that also 3 minus I is a root, and the negative 2i, you also have a positive 2i. So it's not that there's only two roots here, there's a total of 4 roots. We have x equals 3 plus or minus I, and we also have x equals plus or minus 2i. So we've already worked backwards before with real numbers. Now we're going to do it with also complex numbers. It doesn't really change a whole lot. Remember, I represents the radical or the square root of negative 1. So when we dealt with that earlier, one of the things that we talked about doing is subtracting that constant, and then you would just be left with plus or minus that radical. In this case, plus or minus I represents the square root of negative 1, and then you can square, just like we did before, both sides. You get x squared minus 6x plus 9. And then I is I squared. But what is I squared equal to? Negative 1. Because you're squaring the square root of negative 1. And then you add 1, so you get x squared minus 6x plus 10. That represents the quadratic that gives you the roots 3 plus or minus I. And this one doesn't have the constant, so you can go ahead and square both sides. You don't have to add or subtract anything. That'll get you x squared is equal to 4i squared. Once again, I squared is negative 1. So x squared is equal to negative 4. Add the 4, and you get x squared plus 4. So then you'll take these two quadratics and multiply them together to get the polynomial function. So I've multiplied x squared times x squared times 4, negative 6x times x squared, negative 6 times 4, and then 10 times x squared and 10 times 4. And so my polynomial will be written as f of x equals x to the 4th minus 6x cubed, and then I have like terms, so that'll be plus 14x squared minus 24x plus 40. And that will represent my polynomial that will have the roots 3 plus or minus I and plus or minus 2i. The next example we're going to look at is I'm actually going to give you a zero of the function, and I want you to find the remaining one. Now we've done this before, but usually the zero I've given you has been a rational one. I'm going to give you a complex root, x equals negative 1 minus 3i. And the first thing that you should recognize, it is a complex root, so it comes in a pair. So also negative 1 plus 3i is also another one of our zeros. And so that's 2. We have a total of 3, so we're just missing one of them. So how are we going to find that third one? Well, if we know that x is equal to -1 plus or minus 3i, we should be able to figure out the quadratic that gives us that as our solution. So let's go ahead and do the same thing we did just a second ago on that last slide. Add 1, square both sides. That would be x squared plus 2x plus 1. And then if you square plus or minus 3i, that'll give you 9i squared, which would represent -9. Remember, 9i squared is 9 times -1. Add the 9, and we get x squared plus 2x plus 10. This represents the factor of the polynomial f of x. That gives us the two roots. So if we know it's a factor, which means it has a remainder of 0, we should be able to divide the function f of x with my quadratic x squared plus 2x plus 10. It'd be nice if we could do synthetic division, but because it's not written in the form of x minus k and we can't get it in that form, we will have to do long division. So let's set that up. Now once we have it set up and we go through long division, we should expect to get a remainder 0 if we've done our other math correct, and this is true that this represents one of our zeros. So what times x squared gives you x cubed? Just an x. So we'll put the x here. So x times x squared is x cubed. Multiply by everything, plus 2x squared plus 10x. Subtract each one of those terms. The x cubed cancels. That leaves you with 2x squared plus 4x plus 20, carrying down the next term. What times x squared gives you 2x squared? And that would be a plus 2. So that would be 2x squared plus 4x plus 20. And once again subtract, and what you notice, we get that remainder of 0 that we are expecting. So now not only do we know that the x squared plus 2x plus 10 is a factor, we also know that x plus 2 is a factor, which is important because if that's also a factor, then x plus 2 could equal 0, and we know our last 0 of this polynomial is x equals 2. So use the given 0 to find all the zeros. So let's go ahead and write the answer. X is equal to -2 and then -1 plus or minus 3i, and that gives us a total of 3 zeros for this polynomial. Now we've learned about the rational root theorem, which gives us the possible rational roots. The Decartral sign is another thing that gives us more information about the real roots of the polynomial, not just the rational. So if we let f of x be a polynomial function with real coefficients again, the number of positive real roots of f of x is either equal to the number of variations in signs of f of x or less than by an even integer, and I'll talk about what that means. To find the number of negative real roots of f of x, once again, it's equal to the number of variations in the sign of f of negative x. The difference is f of x for positive, f of negative x for negative, f of negative x for negative real roots, but also less than by an even integer. So what does kind of all of this mean? Well, if we take the sign changes in your function f of x, so if you look at this, x to the fifth is positive, negative x cubed, plus 2x squared, negative 2x, and negative 6. Those are your signs for f of x. So where are your sign changes? Well, I go from a positive to a negative, so that's 1. A negative to a positive, that's 2. A positive to a negative is 3. And then a negative to a negative, that doesn't change sign. So that means we have 3 potential positive real roots. Now there's a total of 5, so that makes sense. We could have 3 positive real roots. To find the negative, we have to look at f of negative x. So that means wherever there's an x, you have to plug in a negative x and then evaluate that and see what those signs will be. So right now I'm just plugging in negative x wherever there's an x, and then we'll look at the signs. So this would be equal to, so if you have a negative x to the fifth, that's still going to be a negative. If you have a negative x cubed, that's a negative, but it would be a negative times a negative, so that's a positive. This one will be positive 2 times negative x squared, which is positive, so that'll give you another positive. Negative 2 times negative x is positive, and then you have a negative 6 on the end. So how many sign changes do we have for f of negative x? We have negative to positive 1, positive to positive, none, positive to positive, none, and then positive to negative is 2. So we have a possibility of 2 negative real roots. Now we have a total of 5, so no matter what, these should equal 5. If I have 3 positive and 2 negative, then I can't have any imaginary units for that one. Now, what does that last part mean, or less than by an even integer? Well, what that means is I can subtract any even number to get to another possible one. So if I take 3 minus 2, basically, is our even number that we'll be using, I get 1. So 1 is also a possibility. 3 is the maximum number of positive real roots we could have, but we could also have anything less than an even number. So if I subtract 2, I get 1. Well, I could have 2 negative, which then would potentially leave me with 2 imaginary, once again having to equal 5. So is that it? Well, we could also subtract 2 from the negative. So that would give me 0 negative real roots. But I still have 2 potential for positives. I have 3 and I have 1. So I could have 3, 0, and 1, 0. Now if I want this to equal the possible roots, that would be a 2 for imaginary and a 4 for imaginary on the second one. So you're looking for all the different combinations that you can have. So these are the 4 combinations we can have. We can have 3 positive, 2 negative, 1 positive, 2 negative, 3 positive, 0 negative, or 1 positive, 0 negative. And so that's what Descartes' rule of sign allows you to do. So if you look at the next example, you don't have to add any of your missing terms. So there's no sign change from x to the 4th to 2x squared, and then there is one sign change from x squared to negative 2. So that means there's a possibility of 1 positive, and then on g of negative x, you get positive, negative, negative, so there's only 1 sign change there also. So we have 1 positive and 1 negative sign change with a total of 4 roots. So that means there has to be 2 imaginary. Now on this one, if I subtract 2, I get negative 1. Well, we can't have negative 1 of a root. So it looks like this is the only combination that we can have for this. That means there's 1 time it crosses the positive x-axis, 1 time it crosses the negative x-axis, and then there are going to be 2 imaginary or complex roots to round out the total of 4 roots there. So once again, Descartes' rule of sign just gives us more information about the positive and negative real roots that we will have for polynomials. And then our last example here, once again, is to find all the roots of the polynomial function. So we could start with our list of p over q's, but because once again it's 60 as our factor in 1, there won't be any fractions on this one, so we could probably just graph it on our calculator and find what we feel like is solutions, and then we can use synthetic division to prove that. Now we're looking for a total of 4, but remember we only need to find 2 to at least get down to that quadratic equation so that we can solve it. So I used the graphing calculator and I came up with what I thought was 2 possible solutions. One of those was that x equals negative 2. Once again, that's the factor x plus 2, and then the other one, it looks like, crosses at x equals 3, which would be the factor x minus 3. So those are the factors, but also the roots. So let's use synthetic division to prove this and break down the polynomial. So we'll start with negative 2. It doesn't matter which one you start with. If you have any missing terms, make sure you plug those in. I don't on this one. We'll use synthetic division to find the remainder, hopefully to be 0, and I just got to that point, so the remainder is 0. So we went from an x to the 4th to an x to the 3rd, but I don't know how to solve every single x cubed polynomial. So now we have one more that we can use synthetic division on, and don't go back to the original, continue to use the new polynomial. And so we carry the 1 down, and we have 3, negative 2, that'll give us 10, and once again, there's that remainder of 0. So now we've gone from x to the 4th, x to the 3rd, and x squared. There was not any other place on the calculator that I noticed that it crossed, so I was left with x squared minus 2x plus 10 is equal to 0. So here's my last factor. Since it's a quadratic, I would go ahead and solve it, and we'll see what the last two roots are. So first off, I would always just check to see if we can factor this one. Is there any way we can factor factors of 10 that give us negative 2? And there's not. So once again, we have to figure out another way to solve this one. This looks like another potential completing the square one. So I'm going to subtract the 10 to the other side. Half of negative 2 is negative 1. Negative 1 squared is 1. And so we get that negative 9 on the other side. So now you can see when you go to take the square root that we are going to be dealing with complex numbers. So we get x minus 1 is equal to, don't forget the plus or minus, 3i. Complex numbers come in pairs. And then if you add the 1, you get 1 plus or minus 3i. And those are the last two roots of the polynomial. So just write all your solutions. X is equal to negative 2, 3, and 1 plus or minus 3i. Anytime you're solving these polynomials, you have to make sure that you go through and prove and show me that each one of these are solutions. Part of that is using synthetic division, part of it is solving quadratics as well. And so that's another example of finding all the roots of a polynomial function.